Hello, welcome to Lecture 11, Magnetism. This week, we're going to look at how mass spectrometers, motors, and generators all work. To understand this, we'll need to introduce the principles and laws that describe magnetic fields. And to understand magnetic fields, we'll need to understand the physics definitions of magnetic forces. Our study of magnetism will require an understanding of its relationship to electricity. Hence the term electromagnetism. We begin with the concepts and conventions of electric current. Your understanding of chemistry and the fact that a conductor is made up of molecules which allow the free transfer of electrons from atom to atom will allow you to understand that charge can flow through a material. In chemistry, you think of electrons, the negative charge moving from atom to atom. As negative charge moves left, you could also consider a perspective where positive charge would be moving, and I use air quotes for moving, to the right. So as the left side of the material gets more negative, the right side of the material could be considered as getting more positive. We'll represent that rightward, again, movement of positive charge as I. We can calculate I as the change in charge over change in time. Remember, current is just the movement of electric charge. So in physics, we consider conventional current from the perspective of the flow or movement, again, that doesn't actually happen, of positive charge. So we're always thinking of the positive charge moving as representing our current. In this equation, we measure charge, represented by Q, in the unit of coulombs, which is a capital C. And current has the units of amperes, capital A, and an ampere is just a coulomb per second. Another way that we could represent charge is as the number of elementary charges. The elementary charge carried by an electron is 1.60 times 10 to the negative 19 coulombs. This value would be negative, and it's equal and opposite to the amount of charge on a proton, so 1.60 times 10 to the negative 19 coulombs as positive. We also have an alternate equation that's sometimes useful. We can represent current as N multiplied by Q multiplied by A multiplied by V, where N represents the charge density of the material, Q is just the value for the elementary charge here, A would be the cross-sectional area of our conductor, and V is the drift velocity of all the charges, the speed with which they are able to move through the conductor. As we've begun our study of magnetism with this look at current, many of the current calculations you'll be asked to do are quite straightforward. Fundamentally, our study of magnets will depend on our understanding of their forces applied. So magnets are objects that induce a magnetic field in their surrounding space. Our convention is to represent magnets with a north and south pole. The forces generated between multiple magnets will be relative to the orientation of these poles. Looking at the magnetic force conventions, anywhere we have the same pole in proximity to each other, so north close to north or south close to south, we'll experience a repulsive force. Anywhere that we have opposite poles in proximity to each other, so a north close to a south, we'll experience an attractive force. Repulsive forces will cause an increase in the distance between the two magnetic objects, and as such we'll assign those forces a positive sign, while attractive forces decrease the distance between those objects, and they receive a negative sign. The sign convention you should see is relative to the change in distance between magnetic objects. Now we need to think about magnetic fields. Now in our course we've studied forces by examining their effects. Fields are the tool we use to represent a force in space before we apply them to any object. A field is a collection of vectors that represent the magnitude and direction of a force if an object was present there. To understand fields, Let's think of gravity. Let's look at the Earth, and we know that gravity points towards the center of Earth. So all of our gravity field lines will circle Earth, pointing inward, and with a field, the density of field lines represents the strength. So in the green circle here, we see stronger gravity forces close to Earth. And as we move out and away from Earth, the density of the field lines decreases. So in the red circle, we recognize weaker forces. Now let's consider magnetic fields. In a magnet with its north and south pole, the magnetic field lines go from north to south. Closer to the magnet, our field lines are closer together, having a higher density, implying a greater magnetic field. And the further away from the magnet, the more spread out those field lines are. We represent the magnetic field with the symbol B. The units for magnetic fields are Tesla. 1 Tesla is equal to 1 kilogram per coulomb per second. There's a possible point of confusion I want to address here. When we have a magnet, the north pole is the north-seeking pole. Let's consider a compass in a magnetic field. Here we have the north-seeking pole, or the north pole of the magnet inside the compass. And everywhere we place it on a magnetic field line, it will follow the arrow of that field line. Many students find this confusing as they think of a north pole on a compass pointing towards the north pole of Earth. And this isn't wrong, but you must consider that your compass pointing towards the north pole of Earth is not out away from the Earth or not out away from the magnet, but it's actually right on the magnet. And when we place our compass on this magnet, we see that the north pole does point to the north. So the compass on the magnet would represent a compass on Earth. Now we need to bring our two concepts together. We need to recognize that magnetic fields will exert a force on a moving charged particle. The moving part is important. To understand this force, we need to think three-dimensionally, and this could be tricky. The force will be perpendicular to both the direction of the magnetic field and the direction of the velocity of the charged particle. To begin, we'll consider a side view of what's happening here. So we'll have a magnetic field that is pointing into the page, and we'll represent our charged particle with a velocity towards the bottom of the page. Let's turn our perspective and look at the front view. And here we'll see that same field and same relative direction, we're seeing the field lines move horizontally to the right of the page. But because we've only rotated, the velocity still points straight down. To understand the direction of a force that is perpendicular in 3 dimensions, we have to apply, you guessed it, another right-hand rule. To apply this right-hand rule, you'll use an open, flat hand. You'll point your fingers in the direction of V, and then you'll rotate your hand so that you can bend your fingers towards B. If you stick your thumb out, that will be the direction of F. So in our side view, F is horizontal and it points to the right. And in our front view, F is perpendicular to the page and it will point out of the page. We can also calculate the magnitude of the force using the following equation. The force will be equal to the amount of charge multiplied by the velocity of that grouping of charge multiplied by the magnitude of the magnetic field and the sine of the angle in between the velocity and magnetic field. In our case, that angle would be 90 degrees, but that's not always the case. So force is just the magnetic force. It will be measured in newtons. Q represents the amount of charge we have, so we'll measure that in coulombs. B is the field strength measured in Tesla, and theta will be measured in degrees or radian, whichever information you're given. You need to keep in mind that this convention applies to positive charge. If you have a negative charge, it will reverse the direction of force by 180 degrees. Now it's time to look at some examples. Given a moving charge of a known size and velocity in a known magnetic field, what will be the magnetic force on that particle? Let's bring in a diagram from the previous page. And we'll add to that the size of the magnetic field is 1.5 Tesla, and as we've sketched, it's into the page. And we'll take the velocity of the particle to be 12 meters per second down, and we'll take the amount of charge we have to be negative 1.3 microcoulombs. We can calculate the amount of force using our equation, so we substitute our values, and the angle between the velocity and the magnetic field is 90 degrees. So the sine of that angle is 1, and this term can be dropped. And we need to recognize that our equation is set up to take coulombs, so we substitute micro for its factor of 10, which is 10 to the negative 6. And then we complete the calculations to find that we would have negative 2.3 times 10 to the negative 5 newtons. What about the direction? Well, our right-hand rule says point your fingers towards velocity, bend them towards the magnetic field, and our thumb tells us that our direction would be right. But the fact that we have negative charge says we flip our direction and we add that our force will be to the left. Let's look at a more application-based example. We can apply this knowledge to design an experiment to measure the strength of a magnetic field. First, we fire a known amount of charge into an unknown field, and we do this with a known velocity for our charge. Let's take our charge equal to positive 2 microcoulombs. We'll bring in our sketch again from the previous page. We're going to assume that our magnetic field is to the right, but we'll show that our particle has a velocity down and to the right a bit. So we'll say that its velocity magnitude is 50 meters per second, and we fire it with an angle of 30 degrees to the magnetic field. The second thing we do is we measure the change in velocity of the particle, and we apply Newton's second law, which recall is force is equal to mass times acceleration. In this example, we could say that the calculated force is 4.0 times 10 to the negative 5 newtons out of the page. Finally, we can rearrange the field equation using our measured force, our known charge and velocity and angle to calculate that this magnetic field would have a strength of 0.80 Tesla. Again, using the right hand rule, the only direction that this could be is to the right, as we assumed. Now we will look at how magnetic fields apply to mass spectrometers. So in your fields, you will likely analyze substances with a mass spectrometer. And the physics behind these tools are quite interesting. These devices will control the magnetic field and the velocity of a particle, and that's indirectly. And then they measure a force, again indirectly, to determine the mass to charge ratio of the substance that makes up the particle. So we see that these devices have a fixed magnetic field inside of them, and we can launch a particle into them with a controlled velocity. And because this particle will have a charge on it and it's moving in a magnetic field, it'll have a force. And this force will point towards the center. Because there's a force, we'll see that the path of the object changes, and that means the direction of the force changes. And what we see is that we have a motion that brings the particle over towards this detector plate. In fact, this motion will be circular, and it will have a radius associated with that circular motion. In practice, we control the velocity of the particle by putting it into an electric potential field. The equation that we're going to use here is that the mass divided by the charge will be equal to negative the square of the radius, the square of the magnetic field, divided by 2 times the electric potential we use to accelerate the particle. The radius for each mass spectrometer will be fixed. So as we adjust the potential difference and different substances are entered into the machine, we'll see that with some trials, the force is greater than expected and we don't hit the detector. And with other trials, the force is not enough for the velocity, and again, we miss the detector wide. But with certain trials, we'll hit the detector dead on. we know the electric potential required for specific isotopes to have the correct radius of motion to hit the detector. So when we set our electric potential and we find a detection, we know what the mass to charge ratio is of that particle, and we say that we know the substance it's made of. If we have a miss, then we'll have to run another trial with a different delta V until we get a detection. One concept that's not immediately evident is that a moving charge will produce a magnetic field. Remember, moving charges are current. Thus, a magnetic field will circle a current carrying wire. So if we look at a wire that's carrying conventional current, the movement of positive charges, then the direction of the field is found with our friendly right-hand rule. For this right-hand rule, you'll point your thumb in the direction of conventional current, and your fingers should curl in the direction of the field lines. So for this wire, with current moving to the right, we'll see that field lines come out of the page at the top of the wire and go into the page at the bottom of the wire. And we know that with magnetic fields, the closer to the wire, the more intense the field, and the further we move away, the less intense the field. Another interesting phenomena is that a wire experiencing a changing magnetic field will have a current induced in it. This can be accomplished in multiple ways, which include changing the field itself or moving the wire. In the demonstration on the left, you can see that the magnet is flipping back and forth, which is changing the field and inducing current in the wire, which also provides charge to light the light bulb. Recall, field lines are vectors, so the changes include magnitude or direction, meaning more powerful magnets or flipping magnets both produce this phenomenon. This effect is proportional to the amount of wire exposed, so in the demo you see the coils. More coils mean more exposed wire. Now what about the second way? Moving the wire itself. Well, let's quickly draw a sketch where we have a magnetic field and we have a wire with some charges in it. Now, if we move the wire by giving it velocity, we're giving velocity to all of the charges, which means as the wire moves down through this magnetic field, from what we saw earlier, we would expect to see forces applied to each charge moving in the direction as drawn. Applying forces to the charge in the wire would induce a current. As you may predict from the previous slide, exposing more wire to a magnetic field changes the amount of induction. Conversely, having more coils can also concentrate a more powerful magnetic field. Many devices take advantage of this fact, and they use a device called a transformer to convert current and voltage to different levels. So below you see a transformer with a primary coil and a secondary coil on the left. And we see that this transformer has alternating current provided to the primary coil, which will induce a magnetic field that changes back and forth in the central block of the transformer, and that changing magnetic field will induce a current in the secondary coil. The fact that the primary and secondary coil each have a different number of coils in them means that the current induced will not be equal to the current used to generate. Transformers can step up and step down our current, and they're inversely proportional to the number of coils on each side. So if we take the number of coils in the primary side divided by the number of coils in the secondary side, that will be inversely proportional to the amount of current in the secondary side divided by the amount of current in the primary side. And because current and voltage are related, we'll also see that the number of coils is proportional to the voltage in each coil. Throughout this whole thing, I kept saying coil. N here represents the number of turns in the primary coil and secondary coil. These two terms, turn and coil, get used interchangeably. Throughout this whole lecture, we've seen that we can manipulate the relationship between magnetic fields and moving charges in either direction. And this goes the same for when we try to apply these concepts. We can create a magnetic field or magnetically induce a current. From this, two crucial machines have been designed. First, motors, which use a current to create an electromagnet in an electric field in an orientation that opposes its current position. With that, the electromagnetic electromagnet begins to rotate. So if we consider two magnets creating a magnetic field, and inside of that we place an electromagnet on a drive shaft, using the coils of the electromagnet, we can create a north pole here, labeled at coil 1, which will oppose its proximity to the north pole in the fixed magnet. This will cause the counterclockwise rotation. As the coil begins to rotate, we can use coil 2 to create an attractive force, bringing it closer to the North Pole, increasing the rate of rotation. As the electromagnet continues to rotate, thus turning the drive shaft, we can continue to change the polarity of the coils on the electromagnet, which will again encourage the rotation to continue, and we can harvest all of that new kinetic energy that we've generated in the drive shaft. This is how electric motors turn electricity into kinetic movement. Generators try and do the opposite. Generators will use kinetic motion to rotate coils of wire or a fixed magnet inside of the other entity. Here, we'll take a coil of wire and we'll draw a fixed magnet inside of that coil, and we'll use that external supply of kinetic energy to rotate the magnet. The rotating magnet constantly changes the magnetic field, which constantly induces alternating current in the coil. The principles behind these two devices are not that complicated, though the implementation of them are quite nuanced. It's time to recap what we looked at this lecture. This lecture we explored new concepts related to magnetism. We introduced the magnetic field and understood how it applies forces to moving charges. And we worked with the laws and principles that describe the relationships between magnetism and current, which is the movement of charged particles. With all of this, we applied our knowledge to better understand the machine's motors and generators, as well as the mass spectrometers that we use in the lab.